Hello?
Hello.
Yeah, so I will bring it over there.
Do
Yeah.
you hear us, Moshe?
You didn't reply. Sorry.
No. Can you hear us?
Can you hear me? I hear you.
Can you hear us?
I can.
I guess you can hear us. Yeah. Okay, perfect.
Okay, and you
No.
hear me, guys?
Yeah. We cannot.
We should be able, though, but you're muted. Okay. Interesting. Oh, oh yeah. This is Can you speak?
Hello, hello.
Yeah, perfect.
You
Okay,
can go
now
on.
you hear me?
Yes, we can hear you.
Okay.
So the next speaker is Moshe Goldstein, and he will tell us about a single photon collider implemented by a superconducting circuit from photon instanton scattering to the Wurmla-Dev-Schmidt transition. Please, the floor is yours.
Okay. So I would like to thank the organizers for inviting me. Unfortunately, due to the situation in Israel, my flight has been canceled and I'm participating from afar. I really hope that better days would come soon, and in particular that I could meet you all soon in person. So till then, let me try to tell you over Zoom about the work we have been doing. And as opposed to previous speakers who mostly concentrated on cold atoms, so this talk will be mostly about superconducting circuits and how to use them to see a very interesting effect in which a single photon can collide with vacuum fluctuations and split into several photons in a very efficient way, and how to use that in order to probe all kinds of interesting physics. So this is at Tel Aviv, we have been doing the theory part, mainly led by my PhD student, Amir Goldstein. And this is together with experimentalists who are working in Maryland and then moved to other places, which are Roman Kuzmin, Vladimir Manucharyan, and their group members. And the works I'm going to tell you about are published in a few papers, and some more are about to come out. So let me start with some motivation or general introduction. So we know that a classical system in, let's say, an AMO physics is a cavity QED, a two-level atom or maybe more levels inside a cavity, which you can drive and probe in different ways. And now, more recently, we also have another platform to do the same physics. Instead of an optical cavity, we can have a microwave resonator, which in this case, in this simple superconducting circuit, is just a strip of aluminum. We'll soon have much more complicated resonators due to reasons I will explain. Instead of the physical atom, we have a superconducting qubit. And the advantage of doing quantum optics in a new system is that whereas typically in atomic systems the cavity is small, the cavity is large and the atom is small, and therefore the coupling between them is relatively small, here the sizes are comparable and light-matter interaction is expected to be very strong. And this motivated people to think about various ways to use that to simulate many-body physics. And now there are many nice proposals, some of them related to things that we have heard about, but to implement many-body models like Bose-Hubbard with an effective magnetic field, etc. But when it comes to actual realization, then experiments, there are some experiments which have very large systems, but then those systems are basically quadratic, non-interacting. And when the systems are interacting and when one simulates them, the actual Hamiltonian, not a digital simulation, then usually the sizes are quite limited. This example from a few years ago was 11 qubits. Today we can get more, but not much more. And this is still a system where it's really a few body system which can be diagonalized exactly. So the question is whether, given the current possibilities in terms of manufacturing and controlling superconducting circuits, can we have an interesting system which displays many-body physics and can be actually be achieved in the lab? And the answer is positive. And for that, you need to go to the basics, basically try to go to the simplest many-body system that one can think of, and those are quantum impurities, small systems coupled to a quantum environment. So it could be the spin boson. In the original formulation, it's like, let's say, an atom which can tunnel between two positions in a solid and interacts with a bath of phonons, or the Kondo model, some impurity spin interacting with the Fermi. And in those systems, the bath is large, but non-interacting. The only interacting degree of freedom is some confined quantum impurity. And okay, so this makes the system on the one hand simple and accessible, both experimentally and theoretically, but nevertheless, it doesn't make it trivial. It's still, if you go beyond, I mean, you can treat the bath using some, if it's recoupling to the bath, you can try to treat it using Born Markov approximations, etc., as we have just heard. But oftentimes the coupling is strong, and it's strong enough to give you genuine many-body physics, like non-Markovian physics, non-Fermi liquid behavior, etc., quantum phase transitions. So now the question is whether you can do the same in a superconducting circuit. And maybe first you should ask, why bother doing that in a superconducting circuit? And let me give you a concrete motivation. So suppose I go back to a two-level atom in a cavity. We know that if I send in a photon, I can excite it to the excited state, and then eventually it will decay back to the ground state and emit a single photon. And then I can ask, why won't it emit 3 photons? Of course, their energies need to sum up to the transition energy. Energy has to be conserved, but why not emit 3 photons or more? So 2 might be forbidden by parity, but 3 is allowed. And the answer is that processes like that are allowed, and in principle they occur. The problem is that the coupling of the system to the environment, the electromagnetic environment, is weak. It's characterized by the fine structure constant, which is very small, and this is a higher order process. The probability for that happening is extremely small. But what would happen if we were to live in a world in which the fine structure constant is of order 1? Then processes like that would be as important as processes in which a single photon stays a single photon. Now, if you are a high energy theorist, of course, then this is just a theoretical model or a theoretical scenario to think about, but we are in condensed matter, and then we can try to engineer this kind of system. And then there is a nice insight promoted a lot by Michel Devoret, saying that another way to think about a fine structure constant, if you want to think like an electrical engineer, is to think about it as the ratio between the impedance of your environment. The impedance is not dissipation, it's the ratio between the amplitude of the electric and magnetic field. Or if we have guided electromagnetic waves in a metallic waveguide, then it's the ratio between the amplitudes of the voltage and the current. So it has units of impedance of resistance, but it's non-dissipative. And the ratio between this quantity and the resistance quantum h/4 is squared, 4 because it's 2e. We are talking about Cooper-Person. The ratio between them up to some factors of pi is the fine structure constant. So another way to formulate the question is whether we can get high impedance in some electromagnetic circuit. And this is not so easy, because if you think about geometrical impedance, when we try to change the inductance, we also change the capacitance, and the ratio between them is not so much tunable. And if we put actual resistance, then we introduce dissipation into the system, actual dissipation, and then all kinds of things can happen to your photon besides the things we are interested in. And now the insight is that if you use a superconducting circuit, but you build it smartly, you build your waveguide in a smart way from a chain of Josephson junctions, then you can reach very high impedance. And then if you couple it to some qubit, which serves as your effective two-level system or artificial atom, then you can see very efficient photon synchrony. Now, why does it help you to have your waveguide not just as a strip of aluminum, as people usually do in such circuits, but have it as a Josephson junction array? So some reminder about the basics of circuit quantum electrodynamics. So when we have non-dissipative quantum circuits, or almost like in those superconducting systems, then we can give them a Hamiltonian description. And then we have conjugate variables, the charge and the flux or phase, they are canonically conjugate. And then you can have an LC circuit. This is a simple harmonic oscillator. And you can have a Josephson junction where you still have the capacitance like before, but the Josephson energy is nonlinear, so you can think about it as a nonlinear oscillator. And this is how you build a superconducting qubit. If instead of a single junction, you use a squid, then it's basically like having a single junction, which is tunable. So now when we see those things one next to the other, we also realize that if EJ is relatively large, then our system is going to be stuck near the minimum of the cosine, and then we can expand, and then this is approximately an inductor, but the inductance is not coming from the geometry, from electromagnetism, it's coming from the Josephson energy, from tunneling, and then one can tune that quite independently of the capacitance and reach high impedance. So in more details, if this is a classical transmission line, inductors and capacitors, so suppose we replace them by Josephson junctions, then now we have this Josephson inductance, and it could have a ratio which is quite flexible. The ratio of it and the capacitance could be quite flexible. And then the impedance or the dimensionless impedance, the ratio between the impedance and the quantum resistance can become quite large. So before we start doing anything with that, we need to test the idea that we can actually build a good transmission line like that. And our colleagues at Maryland at the time, they did that. So they built a very long array of superconducting junctions with a few tens of thousands of junctions, length of 1 centimeter, which is coupled to an antenna on one side, and on the other side, it's just a short circuit. And then they can inject microwave energy at given frequency in and measure what is reflected. And then they see a series of resonances corresponding to the different modes. So they have this a very long system, and still they can see the individual modes, and they can even measure the dispersion. Dispersion starts linear, and it curves down as it's expected. So they can indeed build this unusual waveguide with the effective high impedance, or in other words, it's a very slow velocity of light, in the same way that the impedance is sometimes something like 100 times larger than usual. The speed of light is a few hundred times smaller than the usual speed of light. And now we can start doing something interesting, and there are two parts to the story. Hopefully I could cover both, but at least I'll try to cover one. Okay, so, all right, sorry. What happened? Yes. Okay, so now let's go back and couple this waveguide to a quantum impurity or an artificial atom. It's just two Josephson junctions, it's just a squid. So this is this is how the circuit looks like if you think like an electrical engineer. And then, as I told you, the Josephson junctions along the array, we can simplify them. We can think about them as inductors. We are in the regime where they are pretty large. And if this is long enough, we basically live in the regime where the mode spacing in the array is pretty small, and we can think about it in a continuum description. And this is our effective model of the system. So the waveguide has this continuous description in terms of some bosonic field phi. It's basically the superconducting phase. Phase difference is like electric current. And then there is the last element, which has capacitance, and also it has the Josephson energy. And this is a well-known Lagrangian, or the corresponding Hamiltonian. It describes a Josephson junction coupled to an environment, which was studied by many people over the years. It's also like a quantum Brownian motion in a periodic potential. It's a particle in a periodic potential coupled to a bath. Or it can describe an impurity in an interacting one-dimensional quantum wire, provided you use bosonization. So all those systems are quite old. The new thing about our system, the reason, the motivation to study it, is that in all those systems, the environment and its modes, they are just there where people were interested in probing the properties of the impurity. But now we have an implementation of the same system where you can probe the impurity through sending in modes of the bath, sending in microwave photons which propagate, hit the bath, and are scattered. So this gives us a new lens to look at the system. And now let's see why this is interesting. So let us first start from the case where this Josephson energy is also large. And in that limit, or we can go back here, in that limit means that we can map our system to a system which is just quadratic. And then we are going to have modes in the bath. They are just going to be distorted or phase shifted because of the last element. We are going to have this phase shift with this Lorentzian shape, in which appears gamma naught. This is the elastic rate or lifetime. It's nothing dissipative. It's just 1 over the RC, or here ZC time. It's just the fact that if we put some energy in the last element, it will propagate into the array and never come back. So this is an elastic effect. It's still not the inelastic effects I was mentioning before, but this is a purely harmonic system. But we can still study it, or they can study it in the experiment. And in the experiment, the last element is a squid. They can thread flux through it, change its frequency, and follow the frequencies of the different modes. And one sees that those frequencies change. What basically happens is that as the frequency of the last element, the impurity oscillator, crosses the energies of the other modes, then we see those nice anti-crossings, which is nice oscillator physics. One thing it is important still to do it is that it tells you that although the system is long and you couple to it on one end and the impurity on the other hand, and you might be worried that somewhere along the way some junction is broken and then you have no connection, this affirms to you that actually all the modes are sensitive to what is happening here, so there is no cut through the system. But more importantly, if you look at the density of modes, you see this Lorentzian influence of the additional mode, and you see that there are many modes of the system which fall in this Lorentzian, which tells you that your quantum impurity is strongly coupled not just to 1 or 2 modes, but to many modes, something like of the order of 10. So this is more strong in a sense than all the ultra strong coupling that people have been talking about in the past. And therefore, our colleagues decided to use the new superlative and call it superstrong. But still, this is oscillator physics. Now, it will become interesting when we tune the Josephson energy of the last element to be a bit smaller, and then it becomes more an enharmonic oscillator. And then what happens there? So here we had modes, and each one of those modes was represented by a dot, which seemed to indicate that it has a sharp frequency. But actually, if we zoom in, each one of those modes has some width. And now our colleagues plotted again the mode frequencies, but also colored them by the width of the modes or the quality factor. And they subtracted from that all kinds of uninteresting effects. And from that, they got the internal quality factor, which is usually very high, of the order of 10 to the 4. The natural dissipation in the system is very small, but somehow when each mode crosses the impurity resonant frequency, which changes as function of the flux, then the quality factor drops down by a factor of 100 or even more. Just that when it becomes, the quality factor is too small, it's just too hard to resolve it. Basically, there is no limitation on that. And then you can look at different things. You can translate the quality factor into a loss rate. It just means that you send in a single photon and you are not getting it back as a single photon at the same frequency. And that you can translate into an inelastic scattering rate or inelastic scattering probability if you divide it by the mode spacing delta. So this is the inelastic scattering probability, and those are the experimental numbers, and those can reach something which is close to 1. They reach up to 1/3. So up to 1/3 of your photons that you send, they are not reflected as single photons, and they make sure to excite the system very weakly, such that at each given time there is, on the average, 1 photon or less in the system, and still something happens to it and it disappears. And again, this is not usual dissipation. This is something coming from due to the last element. And funnily enough, if we go along this line and we change the resonant frequency and we collect data, this is basically this data, we see that actually the higher the frequency, the less scattering we have, which is as opposed to usual scattering mechanism. And this tells us that this is not just trivial dissipation, this is something interesting happening in our quantum impurity. So what is happening? Well, our last element is a Josephson junction, and it's not quadratic anymore, it's a cosine potential, and this is a non-quadratic, or the dynamics is nonlinear. Now, still EJ is not too large, but it's still pretty large then with respect to EC in this regime. So basically we sit near a minimum and we can do two things. First of all, when we sit near a minimum, still the potential is not exactly quadratic and we can go to the next order term, which is phi to the 4th. And secondly, there could be phase slips, there could be tunnelings of quantum tunnelings of the phase from one minimum of the cosine potential Josephson cosine to another minimum. And now naively, you would think that those are tunnelings, the probability is small, so therefore we should look at the quartic effect. And indeed we did, and the time is short, so let me give you the main message. The main message is as follows, that when you look at the quartic effect and you express it in terms of the modes, you can define some coefficient, some structure factor, which tells you how efficiently does each mode couple to the nonlinearity. And when you plot it, it's only strong for photons which are close to the resonance frequency, which is natural. Only them can really penetrate into the nonlinear element and experience the nonlinearity. But this is a problem, because then in order for the inelastic process to be efficient, the incoming photon should be close to resonance, as we saw in the experiment. But then it splits into different photons, but those photons, only one of them can still be close to the resonance, and the other will be at low frequency, and they couple very weakly. So when you do the calculation, you can find the results, but what you find is that if the experimental rates or the experimental scattering, inelastic scattering probability is here, then the kernel linearity gives you values which are orders of magnitude too low. So it cannot account for the experiment. So what is happening there? Well, we must get back to the phase slips, and this is a bit weird. And the point is as follows. So the phase slip is a complicated process. First of all, it has some dynamics in time, which has, even for an isolated junction, it has some weights and some weights in time. And it becomes more complicated when you couple it to the bath, because then basically all your junctions along the array must react to the phase slip and experience the phase slips themselves. And you can use a crude approximation to approximate that if you just write some cosine term by hand, which does that and represents a facelift which is instantaneous in time, like so. And as I told you, the facelift must occur all along the array because all the junctions are coupled galvanically, and therefore it's going to be a cosine of the sum not of the phases, but the conjugate variable, which is the charge. And now this is a nonlinear term, which basically allows processes when you expand the cosine of a single photon coupling to any odd number of photons. There is still a symmetry, but any odd number is allowed. And the important thing about it is that if you calculate the corresponding form factor, you find that it's large not only on resonance, but also at low frequencies. And the reason is that when there is a facelift, as I told you, it occurs not only in the last element, but it propagates along the array. So it's basically, in terms of spatial dependence, it's pretty uniform, and therefore it has very large overlap with the low frequency modes, which also are almost uniform. They have K, which is close to 0. Now, this is still a phenomenological model. You can do it much more in a much more complete way. You can basically take the instanton calculus and extend it to do a scattering. For that, you need to invent some new formalism I will not go into. But once you do that, you can do the full calculation and compare with experiment. So now let me go back to this plot that I was showing you. So this is the inelastic scattering rate extracted, or probability extracted from the experiment, plotted on resonance as function of the changing resonance frequency. So those are the experimental points. And we have those broad things, which are the theory. Now, they are broad not because we have some fitting parameters. Actually, here we have no fitting parameters at all. So this is a very hard problem to address theoretically. It's just that we plug into the theory parameters extracted from the experiment, and those parameters from the experiment have some uncertainty. So we basically use only parameters from the experiment with their uncertainty, and then we get those theoretical bands. And we can see that in the regime of large enough impedance where our theory is supposed to be accurate, then there is very good matching between theory and experiment. So we consider that explained. In the regime where the impedance becomes smaller and then some of our approximations are not good, then we have a problem, we have some deviation. Actually, now we have some ideas and we have some preliminary results where we can account for that as well. So this is the end of the first part, and my time is more or less almost off, but let me maybe borrow 2 more minutes to tell you something about the next part of the world, if I may.
Just one. We are completely behind.
Hello? Yes, sorry, I hear that
Yes,
someone...
maybe 1 minute left.
What?
Do you hear me now?
Yes.
30 seconds, exactly.
Okay, so,
Yes.
okay, let's say a minute or 2. So, okay, so just something about the second part. So in the second part, we made our experimentalist friends made the junction even smaller. And then basically the cosine potential becomes smaller, the phase can fluctuate a lot. In terms of superconducting circuits, we go from the Transmon regime to the regime of Cooper pairbooks. And then what they find is that if they look at the inelastic scattering, depending on the impedance, it can either become smaller as function of frequency or actually become larger and larger. And if you try to say EJ is small, let's do perturbation theory diverges. And then you might wonder what is happening here. And recall that actually we know that as function of the environment, there should be a phase transition between a quantum phase transition predicted by Schmidt and Bulgadaev many years ago, between for low impedance, basically the bath basically localizes the phase, the superconducting phase near one of the minima. It acts as a dissipation of friction that holds it near one minimum, and then it keeps the superconducting phase well defined and is superconducting. Whereas for Z larger than 1, then the dissipation is not efficient enough. The particle can tunnel, the phase is delocalized, then charge becomes localized, and the last junction becomes insulating. And now people have been trying to do that, to see that using DC measurements, but that was turned out to be problematic, and there is still an ongoing debate today about whether or not there is this transition. And now what we can do now, or what our colleagues can do, is to look at the system using, again, the single photon spectroscopy. And this is nice because as opposed to DC measurement, now you excite the system by the minimal amount, by a single photon. And then what you would expect is that if you have this transition, then your last element will effectively either behave as an inductor if it's superconducting, or as an insulator, as a capacitor if it's insulating. And that should translate into two behaviors of a shift of the mode, and one can see that. But can also see that in the inelastic processes. And here I guess I'll have to stop. So we can actually calculate them, not just approximately, but actually exactly. So it turns out that in the relevant limit, the systems become integrable. Integrable does not mean that inelastic scattering does not happen. It just means that there are integrable or beta ansatz excitations which scatter elastically, but the photons we send into the system are some nonlinear combinations of them. They scatter inelastically, and we can use integrability tools to actually calculate that and find the inelastic rate and compare that to the experiment. So that was a brief overview of the second part, and I hope I was able to show you that using this new tool of single photon probe, this is a new way to look at old quantum impurity physics and extract new interesting information from it. Thank you very much for your attention.
Thank you, Moshe, for this very nice talk.
Wait, Moshe, can you hear me?
Yeah, so sorry, I hear that
Can you hear me
people are
now?
asking, but I cannot really hear them. So someone will have to translate.
Yeah, can you hear me now? Can you hear me? Yes, hi. So thank you very much for the very nice talk. I have a question about the noise distribution in the rest of the environment. So you have an effective impurity, and you have a wire, and the wire is dominated by its own interaction relative to the Josephson energy scales in the system. How do you know what is the statistics of noise in the rest of the world, and whether it impacts your dynamics?
So basically, as I was mentioning before, they started by an experiment in which only basically they, instead of a quantum impurity, they just put where was it? They just put a short circuit, and then here, and then basically you have just the array itself, and they can characterize it and find that you have very nice modes which are very narrow and sharp, quality factor of the order of 10 to the 4. So basically all kinds of effects you are not interested in, they can characterize them and know that they are very small. And then once you couple in your artificial atom at the end, then you have nonlinear effects which are extremely large by many orders of magnitude. So, and also have some new characteristics. For example, the fact that actually you couple less well at higher energies. Usually, if you have something inelastic happening, then the more incoming energy you have, the more inelastic channels you have. And here it's actually the opposite way. So this tells you that it's not some parasitic effect that you are coupling to, but actually the nonlinearity which you introduced by your artificial atom or your quantum impurity, the way you want to call it.
Thanks. If not, due to time constraint, thank you very much for your talk. So we will reconvene in, let's say, 20 minutes. Yes, thank you.
תודה, משה.
תודה. טוב, חבל.
מה?
חבל שמצטרף רק בזום.
כן, זה אכן חבל, האמת שיש לי הרבה שאלות.
כן, טוב, אז אנחנו יכולים פעם, לפחות בינתיים לדבר בזום עד שיצא.
כן. האמת שיש לנו עבודה גם על כזה boundary impurity, אבל אנחנו הסתכלנו על super omic וסub omic environments.
כן, פה האמת, בדבר הזה שאני מדבר זה הכל אומי.
כן.
אבל אפשר להנדס גם דברים אחרים בעיקרון. כלומר, זה גם משהו שחשבנו עליו. אתם חשבתם על מערכת ספציפית מבחינה פיזיקלית או...
לא, אנחנו סתם הסתכלנו על קיין פישר, coupled ל-finite wire עם omic class fluctuations. זה היה הקטע שלנו. אבל בוא אני ארים לך טלפון, כשיתגמר הוועידה, אני נעשה זום ואני אספר לך על זה, ואז... סבבה?
אוקיי, מצוין.
מגניב, תודה רבה.
טוב, להתראות.
ביי ביי.
ביי, thank you.
Okay. We needed this for the sound. Or is it? So no, this doesn't work. So maybe we can use this one. We can just use this one.
Yeah, but for the speaker, it's annoying to.
Yeah. Or either. So I mean, you can take it off, and then walk like this. But other. I don't know why it's not working. I think it's not the problem of this receiver. It's the problem of the part that is. It was on mute.
Hello, hello.
I think we are good.
Yeah.
It's
To leave the audio open so